So I'm not what you would call a Hadamard person. So Hadamard matrices are kind of a side interest for me in my research, but somehow they kind of pop up all over the place, and also they have I have encountered and worked with them a lot of times. So this is, I'm trying to tell you about an instance where Hadamard matrices make a natural appearance in quantum information theory. So I should start by saying that this is joint work with Statvik Singh, who is now a PhD student in Cambridge. So we have a series of papers about this topic, about this type of symmetry in quantum information theory, going from the more mathematical to the more applied to quantum information theory. But these two are the ones that I will be discussing mainly today. So here is the plan of my talk. So I will start rather with basic things. I will tell you about this idea of symmetry. So looking at objects in quantum information theory which have some symmetry, which are much simpler and easier to analyze. And then I will move from this. I will look at a particular type of symmetry given by these diagonal, unitary, and orthogonal matrices. And then I will analyze in parts 3 and 4. I will analyze two types of objects in quantum information theory enjoying this symmetry. The first one are positive semi-definite matrices. As you might know, this notion of positivity plays a fundamental role in quantum theory. And the fourth one are unitary operators, that are the evolution operators in quantum world. And here, Hadamard matrices will make a guest appearance, and I will discuss them in relation to these objects, which are called dual unitary matrices. Which I heard that tomorrow there will be another talk discussing these, so you will get an introduction, and hopefully tomorrow you will learn more interesting things about these dual unitary matrices and how Hadamard matrices appear in this business, and some kind of trivial observations we have made about these the Hadamard matrices appearing here, and some open question that I hope you might help us solve, or maybe it's some kind of already known results. So I'm looking forward to get your feedback on this last point. Okay, so let me start with some generalities about quantum information theory. So as you know, I will be looking at, in quantum information we have two types of states. People talk about pure states, which are vectors in a Hilbert space, but we also like to work with these more general objects called density matrices. So these are positive semi-definite matrices, rho, which have trace 1. So, you might think of these density matrices as some kind of non-commutative generalization of probability vectors. So indeed, the eigenvalues of such objects are probability vectors, but they are matrices, so they have this kind of non-commutativity. And so in quantum we have this unitary. So when states evolve in quantum theory, we model this by a unitary conjugation. So basically here, so U is a unitary matrix, and we look at this action by conjugation on the set of density matrices. And of course, we would like to look at a special subset of states which have a kind of symmetry, meaning that they are left invariant by a certain set or subgroup of the unitary group. So here is a trivial example, maybe the easiest one you could think of. So if a matrix X is invariant under all unitary conjugation, then X must be a multiple of the identity, so a sky matrix. And moreover, if you want to have your X be a density matrix, then this normalization condition forces this constant that we're in front of the identity to be 1/2. So you see, if I have imposed this very large symmetry group, the whole unitary group, and I have been left with very few objects which enjoy the symmetry. So let's move to a more interesting situation, that of bipartite operators. So now things get interesting in quantum theory when you don't have one Hilbert space, but you have two Hilbert spaces, and you look at the tensor product. So in most of this talk, I'll be concerned with this bipartite setting, where I'm looking at states which are shared by Alice and Bob. So Alice has a d-dimensional subsystem. Bob has a d-dimensional subsystem. And these states are just, again, they are density matrices, so they are positive semi-definite and have trace 1. They live in this larger matrix algebra of size squared. And the way I will be drawing these states as these boxes with 2 inputs and 2 outputs. So the top right input belongs to Alice, top left output it's her output, Alice's output, and Bob appears in the bottom side of this.
It goes the wrong way. You put the input on the left and the right.
No, I mean, this is this is the correct. Your way is the wrong way because I mean, this I'm always having these discussions, these philosophical discussions. But when you multiply operators, you always do it from right to left. So we write mathematics from right to left and English from left to right. People in quantum circuits, they do it the other way around, but they are wrong. So this is the problem. Of course, you can do it. And people from Israel write also Hebrew.
They have the same discussion in Europe.
If it's an invertible operator, it doesn't matter.
Good. So in any case, my inputs will be on the right. So here are 2 examples of these states, 2 fundamental examples. The first ones are these states called separable. So separable states are in kind of way the classical states in quantum theory, in the sense that they are just mixtures, so complex mixtures of a state on Alice's side tensor, a state on Bob's side. So you see they have this feature that there is this separation between top and bottom, between Alice and Bob. And these are states which you can, you can create at a distance between 2 labs. So Alice prepares the state for A, Bob prepares the state for B, and then they do this complex mixture. Sum of pi rho AI tensor will be. And we are mostly interested in states which are not like this, so which have this kind of non-classical correlation. These are called entangled states. And here is the most famous one. It's called the maximum entangled state. It has this. So it's a rank 1 projection on this vector sum of II. So here I'm using quantum notation. So when I write I, this is the ith element of the canonical basis. So you see this is this rank 1 projection on this sum of II. So in diagram world, it's depicted like this. So you see here Alice's input is perfectly correlated to Bob's input, and the same on the opposite. So this is a state which is, it doesn't exhibit the separation here in the middle between Alice and Bob. So it's a state which is called entangled because you cannot write it like this as a complex mixture of products. So most of in quantum information theory, we like a lot to talk about entangled states, and we like to know if you give me a state, is it separable or entangled? And this kind of questions are of fundamental importance to us. So now let's look at symmetric states. So what happens when I impose the symmetry condition? So this is what I'm doing here. I'm taking a bipartite matrix. So this is box X, 2 inputs, 2 outputs. And I'm asking that for all unitary matrices, when I act with U tensor U on the left-hand side and the conjugate tensor product on the left-hand side, I ask that this operation lives invariant of my state. And it turns out that if I impose these conditions, the set of solutions is 2-dimensional. It's a vector space of dimension 2, and it's spanned by the identity matrix and this other matrix, this other bipartite matrix called the flip or the swap operator, which does what its name suggests. If you give it a tensor product, it just changes the order of the factors. So here are how they are represented in picture world. And you see the idea, the philosophy behind this result is that these are basically the only diagrams which will allow these U's on the left-hand side to cancel the U stars on the right-hand side. So the simplification right to left is easy because you can just move the U boxes along the wires and they cancel each other. But it's a very easy result in representation theory that the commutant of the algebra U tensor U is given by these two operations, these two operators. So again, the idea is that we have the symmetry. We get a 2-parameter family of states. Now, if you impose that your state is, if you ask that your state is a density matrix, now it turns out that when you have density matrices, it makes more sense to look at another type of tensor product. Instead of looking at U tensor U, I look at the U tensor U bar. I don't want to get into the reasons, but it makes more sense to use this one than the other one. What happens is that if you impose the symmetry, so u tensor u bar rho, the adjoint of u tensor u bar equals rho, this means that rho will be a mixture of two states, the identity state and the maximal entangled state that I showed you before. So now basically the only states which enjoy this symmetry are the states on this green line here. They are called isotropic states. They are very well studied in quantum info. So because they're very nice because they are somehow a mixture between the most entangled state and the less entangled state, the most separate state. So you can have this interpolation between these two states. So of course people like to study this kind of, you have these interpolation states. So they are very nice. So here's how isotropic states are the unique symmetric state with respect to the symmetry u tensor u bar. Again, so here we have a one parameter family of quantum states which are symmetric. So this is good because we have reached these very interesting states, but we would like to have larger family of states which we can analyze. So this is what we are going to do. And the idea is that when imposing this full unitary symmetry, we got interesting families but with few parameters. If we want larger families, we should somehow relax the symmetry. So we should have less symmetry, so a smaller subgroup. And why not look at this torus group? So these are just the diagonal unitary matrices. So from now on, I will be focusing on symmetry, but not with the full unitary group, but with the subgroup of diagonal unitary or orthogonal matrices. So if you look at unitarys, basically you have phases. If you look at orthogonal matrices, you have signs to the diagonal. And these kind of, since these matrices are diagonal, the way they are represented in picture world, I'm just having this line, which means that input has to be, input index has to match output index. They are diagonal, and I put on top this vector u, which gives the corresponding phase, right? So the element uij is just delta ij times the corresponding entry of a vector now, small u. So let's play the same game. Let's look at what are the matrices which have this symmetry, which have this diagonal symmetry. And of course, we start with the simplest case. No thanks for that. We just have one matrix space, and you can see that you gain something, because if I impose this diagonal symmetry, so if I ask that ux u star equals x for all diagonal unitaries, then I get that the only condition that x needs to satisfy that it needs to be diagonal. So it's a very simple computation. So remember that before the symmetric matrices, when I asked for the full unitary group invariants, were just the scalar matrix, so multiples of the identity. Now I get a larger set, which are the diagonal matrices. So we gain something. Now let's move to the case which is interesting for quantum, because we have tensor products, these bipartite operators. And this is like a definition slide. It's a bit dense, so let me tell you a bit what we want to do here. So we want to impose basically consider three types of symmetry. The first one is when I do u tensor u x the adjoint of u tensor u. And I ask this to be true for all diagonal views. The second case, it will be useful to you look at quantum states. I will be imposing this u tensor u bar symmetry. And in the third case, I'm using orthogonal matrices, so there is one definition. And we call this LDUI, local diagonal unitary invariants, CLDUI, conjugate local diagonal unitary invariants, and LDOI, local diagonal orthogonal. And these are how these conditions look in picture. You see, before I had the matrices U acting here, 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 and here. Now, since the U's are diagonal, I just put this small vector U on top of the ones. Good. So, results. Matrices satisfying this diagonal unitary invariants have so the set of these matrices has many more parameters than in the unitary case, and this is how they are parameterized. So I'm looking at this CLDUI invariance because I think it's the easiest one to. They are kind of all more or less equivalent, but it's the easiest one to explain. So remember, CLDUI means that u tensor u bar x, u tensor u bar conjugate equals to x for all diagonal u. And a matrix X satisfies has the symmetry if and only if there are two matrices of dimension d. So what's important here, remember that X is a bipartite matrix, so it has size d squared. But symmetric X's are parameterized by two d by d matrices. So smaller matrices, they need to satisfy this technical condition that they have the same diagonal, which I call delta. And if you like, coordinates, you can write the entries of X in terms of the entries of A and B like that. But if you like pictures, this is how all symmetric matrices look like. So symmetric matrix X is built of two matrices, A and B. And you see I'm using A to create, coordinates which have I equals K and J equals L on the bottom. And I'm using B to create coordinates which have I equals J on the left and K equals L on the right. And then somehow, because I'm double counting, I have to subtract this common part where all the indices are. So this gives you all the symmetric matrices with this diagonal symmetry. And again, the important point is that somehow I have order 2D. I have 2D minus D parameters. Whereas remember before I just had 2 parameters. So I have less symmetry. So larger class of symmetric matrices, and they have 2D parameters. Okay. And you have similar formulas for the other types of symmetry. So maybe this is the smallest group because it's the orthogonal group. And now these in the orthogonal case they are parameterized by 3 matrices which have the same diagonal, and somehow each of them takes care of all possible pairs of equal entries, but it's kind of technical. I don't want to go into this because when you see these coordinates, basically, it's hard to keep track of them. So I'll be mostly focusing on pictures. So here are some examples. So the identity matrix is of this form, and it's of the form when I take A equals to be this J matrix. This is the all ones matrix, and B equals the identity matrix. So when I put this J matrix, in picture world, it's represented by these 2 vectors, 1, 1, and their tensor product. So because every entry is 1 times 1, and I'm using this, this construction, this A-type construction, where this part here goes onto the top and this part here goes into the bottom, and you see you get the picture on the left-hand side, which is the identity matrix. The same for the maximal entangled state. Remember that was the picture we used for the maximal entangled state. But now I'm using this B matrix. So I'm putting this 1, 1 instead of the B matrix, and you see the one will give you, this thing will give you this part here, and this thing will give you this part here. And the flip operator is of LDUI type, so I'm using this C matrix, which I didn't talk about, so I don't want to go into much details. But just to point out that these 2 pictures, so this of course generalizes the full unitary symmetry, which is of course it's a set which have this full unitary symmetry are a subset of our set. So and they appear using these simple I and J matrices. So it's a very nice set. It's a very nice subset. Okay. Now this was just no structure, just linear algebra, vector spaces, nothing too interesting. So let's look at structure now. Let's look at, and I'll be looking at 2 types of structure, so positivity and unitary. So let me start with positivity. Also check time. So now I'm looking at, so I'll be denoted by XABC, the operator which comes from these matrices ABC. So this is one of my diagonal symmetry operators. So it turns out that I can read many of the properties of X in terms of the properties of the smaller matrices ABC. And this dictionary is very nice. So for instance, if I want my matrix X to be self-adjoint, then A needs to have real entries, and B and C need to be self-adjoint. And now this is the interesting part. If I want my big D squared by D squared matrix X to be positive semi-definite, then 3 things need to hold. First of all, the entries of A need to be positive real numbers. B has to be a positive semi-definite matrix, and C has to satisfy some kind of determinant condition. I will show you this why this is the case. But I will be interested in mostly in these CLDUI operators, in which case C is diagonal. So this condition will not it will be automatically satisfied because the only thing which matters is I equals J, and A and C have the same diagonal. So this is the condition of the operator. So basically, for the CLDUI operators, the fact that XAB is positive semi-definite corresponds to 2 different positivity conditions for the parameter matrices A and B, A has to be positive in the sense that its entries need to be positive, and B has to be positive in the sense that it has to be positive semi-definite. So this means that this positivity of X corresponds to A belonging to the cone of positive, vectors with, matrices with positive entries, and B to belong to the positive semi-definite cone. So we have a mixture between these two different kind of notions of positivity. One, the usual type of positivity, and the other one, positive semi-definite matrices. And this already allows us to prove a result which was already known in a different form, which is the following one. So imagine that I'm taking A equals B. I want to intersect kind of these two positivity conditions. So I have a matrix X, which is of the form XAA. It's built off of the same matrix. And I can characterize the separability of this matrix, this bipartite operator X, in terms of the matrix A. And the condition is that the matrix A should be completely positive. So this is a notion which has been studied a lot mainly in optimization theory, but lots of branches of mathematics. And completely positive means a little bit more than positive. So a matrix X is positive semi-definite if you can write it like RR star adjoint. Sorry. So now we ask a little bit more. We ask that the matrix, there is such a decomposition where the matrix R has non-negative entries. So this is the condition, important condition here, that there is a decomposition of the form A equals RR adjoint, but now with R being real and with non-negative entries. So in particular, this tells us that A itself has non-negative entries. And these two conditions, are the same for D equals D smaller than 4. So any matrix A which is positive semi-definite and with non-negative entries can be written like this. But in dimensions 5 and more, there are examples which cannot. So this is it's hard actually to test whether a matrix is completely positive. Such decomposition exists, and it's actually an NP-hard problem to detect whether A is like this, is completely positive. And this I want to make the point here that in general, the separability, detecting whether a state is separable, deciding whether a state is separable or not, it's an NP-hard problem. And my point here is that it's still an NP-hard problem for these symmetric states because of this result, because of this relation with complete positivity, which was proven earlier to be
you don't restrict R to be a square matrix, you just can D times F. Do you need to restrict here?
No, actually, this is a typo. Thank you very much. Yes, it's a typo. So R doesn't have to be square. So the other dimension of R, which is the number of columns, would correspond morally to the number of terms in the separable decomposition of my matrix. But indeed, this is wrong. Only R should be in the set of MD times some other equal. Thank you. Good problem. So this shows somehow that this family of CLDY states, and moreover the subfamily of CLDY states which have A equals B, it's big enough in order to contain some interesting physics, in the sense that it's hard to say whether the state inside is separable or not. This was not obvious. This was not the case for the isotropic states, this one parameter family that I mentioned before, where it's very easy to decide the entanglement. So this shows that this is kind of advertisement for the fact that these families that we are looking at are rich and somehow you see in general detecting separability or entanglement, it's a hard problem. You don't have many tools, but here it corresponds to something which has been studied before. So it's kind of there are some tools that you can use to analytically tackle some of these questions. Okay.
The question.
Yes.
So completely positive matrices, they generate a cone, right? But they don't, in that cone, not every matrix has that product. So do you mean that A really has to be the product of two such things, or within the generated cone? Or maybe
I think this is enough, because you can do like if you have two, if you have A and B which are like this, you can take, you know, an R which is like with blocks, and you can build the sum. So I think completely positive matrices form a cone, but
if you allow the
yes. So this goes back to the remark, of course. Yeah. So I apologize for this. This is like it's not a typo. It's a huge mistake. So R should be allowed to be very tall. I mean, yes, of course. Yes. I apologize for this. Good. Now let me move. So I want to really tell you about Hadamard matrices. So this will be like on the last slide. So my talk was it's a story which culminates with Hadamard matrices. So the Hadamard matrices appears not in this positivity business, but when you look at evolution of unitary operators. So now we ask the same questions. We have these symmetric matrices. What are the symmetric unitary matrices? So here's an observation. If you remember from when I gave you the formulas for this matrix X, you saw that the entries. So this matrix S is very sparse. So it has non-zero entries only when two of the coordinates are equal. And so you can imagine that it has a block structure, and this is the block structure of the matrix X. So if you have three parameters, if these three defined matrices ABC, the matrix X has a block decomposition where B appears like a full matrix. And then you have these other 2 by 2 blocks, which are built out of the entries of A and C. Okay. So you see that it's very easy to compute the spectrum of this matrix in terms of the spectra, in terms of the spectrum of B and the entries of A and C. And then you can check unitarity. So when is such a matrix X and C unitary? So it's very easy to do. I mean, B needs to be unitary. There is this condition that somehow the lines, the two rows or columns, I don't know what I'm doing here. So I think I'm doing rows have to be orthogonal and this normalization condition. So this is how you decide. If you give me ABC, this is how I decide whether the matrix X is a unitary matrix. Whereas this doesn't look, this is less appealing than what we had before for quantum states, but that's life. Let's go on and see what happens. Oops. Oops, I'm going the wrong way, sorry.
You see the input output really matters, which way you are going with the input output. You can see on your
Yes. So now, finally, I will introduce some other objects. So there was a lot of definitions. I apologize for this. And Hadamard matrices. So Hadamard matrices will appear. So for this, I need to tell you about dual unitaries. So what is a dual unitary? So a dual unitary is a unitary matrix, U, which has the extra property that when I permute two of the legs of this tensor U, the resulting matrix will still be a unitary matrix. And in this notion of dual unitaries, I need to permute this bottom left and top right legs. So dual unitary means square dual because U has to be unitary. And this realigned matrix obtained by permuting two of the four legs of U also needs to be unitary. Here is an example. The flip operator is a dual unitary because, of course, it is a unitary matrix, the flip. And you see when I'm permuting these two legs here, it's invariant, so nothing changes. So it is a dual unitary. However, the identity operator is not a dual unitary because look what happens when I permute this leg here and this leg here of the identity matrix. I get its maximum entangled state. And you know, its maximum entangled state is a one operator, so it's not a unitary matrix. So think of the flip as the most like the typical dual unitary matrix. And now I can ask the question. So these are why people are looking at this. There are many reasons. Maybe one of the most recent one is that kind of these if you build these quantum circuits using dual unitaries, you can do a very fine analysis of the correlations that appear in the entanglement evolution in these circuits. So they have been recognized like a very nice toy model for studying these quantum circuits. So there is a motivation coming from quantum computing, let's say. Now let's look at our class. When is a unitary from our class a dual unitary? And these are the conditions. since I'm not doing so well on time, let me. So conditions are of the same type. So we kind of have the unitarity condition, a normalization condition, and the orthogonality condition. But if you now restrict to LDUI, so this means that B is diagonal, so B doesn't appear in this business, then the condition is that the entries of my matrix C have to be of modulus 1. And now you see we are getting closer to the Hadamard condition. Before Hadamard, I have to tell you about another condition. So again, sorry about some things. This will so I heard that this will also be discussed tomorrow, so maybe it's not so bad. So I'm going to tell you about the entangling power of a bipartite unitary matrix. So as I told you, these unitary matrices are they can think of as evolution operators, so as quantum gates. And they are bipartite, so they act on these two tensor product of two Hilbert spaces. And we want to talk about entanglement between these two tensor factors. And one way, very easy way to measure entanglement is this two entropy or linear entropy. So if you have a bipartite state, you can build this number. You can contract 4 copies of your state in this way, and you get a number between 0 and 1. And this number will tell you whether your state is entangled. I cannot tell you much more about this, but this is somehow a very quantity which is very easy to compute. It's a degree 4 polynomial in your vector, and it tells you about whether this thing is product or not, so whether it's entangled. And now we have this notion of measuring entanglement, and we have this evolution unitary, and its entangling power is how much entanglement can it create starting from a separable state. So this is what I'm doing here. I'm looking at a product state, a separable state, phi times psi. I'm applying my gate X, and I'm looking at the entanglement of this output state. So in input, you put product, and you look how much does it gets entangled in the output. And I'm taking an average over random input vectors minus. And then I'm normalizing so that this quantity is between 0 and 1. And this is called the entangling power of my unitary gate. So it has this very nice properties that, for instance, if my gate is a tensor product of unitaries, it will not entangle, so it's 0, and all this kind of the things you might expect. So of course, then you can ask which are the unitaries which have the largest entangling power. And this is what we are doing with in our paper. We are looking which among our symmetric operators have the largest entangling power. And the answer is that the ones which correspond to C being a complex Hadamard matrix. And although there is no fixed dimension, there is no symmetric matrix which achieves this maximally, this largest entangling power at fixed dimension, we get the result that when you let the dimension grow, my remote vibrated, so maybe this means that I have to stop. I don't know what it means. At least we get this asymptotically. So in our symmetric family, you can always find you can find one at each dimension, and which gets better and better at and when you do the computations, this average with respect to the Hahn measure, you find that the entangling power of X is related to this quantity associated with the matrix C. So remember, C has entries of modulus 1. And the quantity we are looking at is this kind of Shelton 4 norm of my matrix C, which is just the sum, so the sum over all pairs of rows of the scalar absolute, so the modulus square of the scalar product between all pairs of rows. So the question would be how to minimize this quantity, and of course you know that this quantity is here. So I can copy it. You have the formula again. This is the one that we are looking at. Maybe this is the most nice expression. So you see, for I equals j, I get d squared. I get d. So I get so this quantity it's larger than d cubed. And it is the cube when you have a Hadamard matrix. The question is now what happens when I ask that my gates have real entries. So this corresponds to C being a real matrix. So I'm now thinking about real Hadamard matrices. And I try to minimize this function for dimensions which are not multiple of 4. So basically the question is, among all sign matrices, which are the ones which have the smallest scalar product of rows? And you can enumerate them, and you can do some numerics for dimensions which are not multiples of 4. And we have found these the values. I mean, what is the minimal value of this quantity? What we notice is that you can always find a matrix, a sign matrix C, such with the property that so the one which minimizes this quantity H are always such that when you take odd D, the number of the scalar products between rows are exactly 1. You know, they cannot be 0, but they're exactly 1. So these are always the one which you can always find one which minimizes, which has this property. And we are wondering whether this quantity H, I mean the minimum of H over all sign matrices is known, and whether we can say anything about minimizers of this H, in particular whether you can always find a minimizer which has scalar product equals to 1 between rows. So they're exactly just one position where things go bad somehow. And with that, I would like to leave you with this open question, and thank you for your attention.